This set of directions comes from section 4.1 in your book. It asks you to find the zeros of a function and state the multiplicity of each. So we're going to look at a couple of example problems. Let's take a look at this first one. Notice that the function is already completely factored for you, and you know that because you see parts of the problem in parentheses. They're sitting side by side. This indicates multiplication. There are no signs, addition, subtraction, between the parentheses. That means it's already been factored for you. When the problem has already been factored, if you want to find the zeros, you just set each individual factor equal to 0 and solve. The exponents in each set indicate the multiplicity of each. Now here I've taken each factor and I've set each factor equal to 0. So we're going to solve each one individually. If I solve this one, I'm simply going to bring the 5 across the equal sign. Remember, when you bring something across the equal sign, it changes its sign. So we have x equals negative 5. On this one, I bring the minus 4 across, and I have x equals 4. This one, I bring the 1 across, and I have x equals negative 1. Those are the three zeros of the function. Negative 5 is a 0, 4 is a 0, and negative 1 is a 0. That means that this function crosses the x-axis at each of those points on the graph. Now, multiplicity tells you how many times this happens. There are turns involved. When you have the graph, it's going to touch it and pop back up. The multiplicity tells you when this happens and how many times. It's usually involving this exponent. See, here's an exponent of 3. It was on the x plus 5. That means that this one has a multiplicity of 3. It is that simple. This one had that invisible 1 on it. So this one has a multiplicity of 1, and we don't have to write it if it has a multiplicity of 1. We can just leave it alone. This one has a 2 on it. So this one, this 0, has a multiplicity of 2. It really is that simple. You just look at the exponents on them. If they're already factored. If they're not factored, you actually have to do the factoring. For instance, this one has not been factored. Notice it has a 4 on the front of it. Until they're factored, the exponents have nothing to do with the multiplicity. The exponents in the front will tell you how many zeros you have. So we're looking for 4 zeros in this problem. Now, some of them, granted, could be imaginary zeros, so you won't always find 4 zeros when you're doing this process. But the first thing you want to do is you want to factor. This is a trinomial. Even though it has a 4 in the front, it is a trinomial because it has 3 terms. So we're trying to find factors of 9 that add up to negative 10. What are the factors of 9? Think about that. 1 and 9, 3 and 3. There's not that many to choose from. 1 and 9 are factors of 9 that would add up to 10, but we have to make sure we get the signs right. If this is a plus 9, that means the signs are the same. So it's got to be a plus 1 and a plus 9, or a negative 1 and a negative 9. Most of the time we can get that part right. A negative 9 and a negative 1 would give us negative 10. We have to be very careful, though, because this 4, that's the exponent, is something we're not used to. Normally, we slap an x in each set of those parentheses, because normally that's a 2 up there in the front, and we split the 2 into x and x. Well, this is a 4, so what we're going to do is we're going to split the 4 into 2 and 2. If it had been a 6, we would split it into 3 and 3. If it had been an 8, we would split it into 4 and 4. You won't have odd numbers when you're trying to factor these trinomials. They'll always be even. Now, each of these factors can be factored one more time. Each of these is a difference of squares. X squared minus 9 can be factored into x plus 3 times x minus 3. And x squared minus 1 can be factored into x plus 1 times x minus 1. So now we have our 4 factors here. You set each individual factor equal to 0 and you solve. If I set x plus 3 equal to 0 and I solve it, I'm going to get a 0 of negative 3. There's no exponent except the imaginary 1 on each of these, so all of these have a multiplicity of 1. This one we would get a 3 out of it if we set it equal to 0 and we solved it. This one a negative 1. This one a positive 1. So we have 1, 2, 3, 4 zeros, which is what our exponent told us in the beginning. Those are the 4 zeros for this problem. That means that's where the graph would cross the x-axis at negative 3, positive 3, negative 1, and 1. Each have a multiplicity of 1 because each factor has an exponent of 1. Again, remember it has nothing to do with this exponent. It's the exponent after the problem has been factored.